Okay, what I want to do in this short video is a bit tangential to kind of what we're doing, but it at least illustrates, in my opinion, the importance of abstract Fourier series in Hilbert space, or not Hilbert space even, in an inner product space, and in particular, in a finite dimensional inner product space. This is quite important. And so, what do I want to prove? So, what we're going to talk about is best approximation uh, in inner product spaces. I'll just best approximation. So, here's the idea. So, let's say we have an orthonormal set, or an orthonormal set. Right. So, let's say this is orthonormal, and I have Fourier series kind of in mind. So we'll go from minus n. And let's say I is an inner product space, does not have to be complete, so we do not need a Hilbert space. Let's say this is orthonormal. So if X is in I, so X could be in the span of this, it may or may not be in the norm. So actually, we could even have that X can be written as an infinite series that converges in the norm associated to I. But in general, let's just say we have X and I. Then the claim is as follows. So let's say as before, Sn x is exactly what we had before. So this is just, you can think of this like the partial Fourier sums. So x, en, en. So this here is less than or equal to following x minus the sum here for any complex numbers Cn whatsoever. That's the yeah, and in particular, let's say we want to solve the optimization problem of minimizing this here. So we have the set here, and we want to approximate x by these kinds of finite linear combinations of the ENs. So let's say we want to approximate f by a finite linear combination of the ENs. So how do we best do that? Well, we do this best by this. Right. So in other words, using kind of data science parlay, further, so if you've never seen this, argmin, I think everyone has, but if you haven't, so what we're saying is the CNs that optimize following, particular minimize the following, exactly what this is. Are the Fourier coefficients. X En. So yeah, this is a bit messy, but this is n equals um, looks a little weird. Well, probably it's fine. N equals minus n. Yeah, so right, can't do any better than these Fourier coefficients. This Fourier coefficient solves this minimization, right? And this is like Bessel's inequality, and that the proof is really incredibly simple. And I think it's nice because it really illustrates the power of working with an inner product space for practical purposes, for practical approximation purposes. And when you leave an inner product space, well, things just get that much harder, fortunately, but that's life. Um, right. So the proof is extremely simple. What I'm going to do is write this here in the following way. So I'm going to add and subtract the partial Fourier sum. I guess in theory it could be the actual Fourier series because it is possible that X is in the finite span of these ENs. Doesn't have to be. Well, if I add this, I have to subtract it. Sorry, if I subtract it, I have to add it. So it would be this here instead of Cn be the coefficients minus Cn. Right, so that's an N here. Cn um, this minus Cn. Yeah. Right. So let's call this U, and let's call this V. All right, so I claim that U and V are orthogonal. Right. And then we're going to use Pythagoreans. Okay, really not much to this. Probably easiest to just this. Uh, we get this. So this is U. So I think it was only recently, for some bizarre reason, only recently that you were able to use a bigger eraser. Okay, so remember that's U, and this is V. bigger. I mean, you could probably even just immediately see why this is true anyway. Um, Much to it. I mean, I'll do the computation. Really just distribute that to this. All right, so we take this, distribute it here. I'll do that in orange, why not? So that's going to be the sum here. X. So I'm going to pull this out, complex conjugate, because it's going to be in the right spot. Okay, and then it's X En, and then do this whole thing here. And sorry, one of these has to be M. So I already did this as N, so let's do this as M. And we've done this before. What's this here? That second. Yeah, because this is orthonormal, we got a lot of cancellation on. M equals minus N. N equals minus N. N. So again, we have this pulled out complex conjugate. Because it's on the right. But otherwise it's XEM. This is on the left, so actually, sorry, it's a minus. Would not be in a good place. It goes to plus, minus here, and so it is minus. Do want it to be the same thing. But yeah, this is on the left, so there's no complex conjugate. So it's EM. Right. And of course, this equals 0 if N is not equal to M, or rather M. So M has to equal N for this to be not 0. So 1 M equals N, 0 if M is not equal to N. So I'll just do this in black, like rewriting everything. So it's going to be this sum here. Actually, yeah, just copy it. And I'll just do it in blue. Yeah, I think writing everything out with these little computations is probably the most annoying part of proof, not even proving it. Funny, but right, so M has to equal N. So sum n equals minus n. Got the same thing here. That didn't change. Well, this is 1 and this is x e n. So, right, they are literally the exact same thing. So you're taking this, subtract this, it's exactly the same thing. And that's it. All right. What does that tell me? Well, I can use Pythagorean's theorem, right? So this here can be written as u plus v. So in particular, I want to take the norm squared. And remember from AMAT 220, because these are orthogonal, I can write this as, and we've basically finished the proof if you think about it. Well, we have finished the proof if you really think about it. Why? Because, actually, let me move that over here. Plenty of room. Through here. Try to be a little efficient. Okay, right. So, right, well, what is U and what is V? So, right. So this is U. Let me get rid of this. Yeah, and the funny thing is we can basically do both of these at the same time, both claims. Well, sorry, this is U right here. And I'll just switch to N. Okay, and right, what is V? V is exactly this here. So the idea is that no matter how you pick the C's, and this is the whole punchline, you can never get rid of this, period. I don't care what the C's are, you always have this by Pythagorean's. The best you can do is, well, minimize the second part, which is obviously minimized by setting Cn well, sorry. Yeah. So actually, because this is orthonormal, what we could do is we can take this a step further. So we actually know what the second thing is. second. Make this a little smaller for a second. Right. So because the ENs are orthonormal, we know that this is the following. Just again, just linear algebra, basic linear algebra, because this is orthonormal. It's just going to be, if you want to check it, by all means, check it. This one. Yeah. Right. So again, we've immediately proven part of it. This is certainly less than or equal, sorry, not less, bigger or equal to, because this is non-negative. Right. So no matter what, this, no matter what, is bigger or equal to this. You just can't do better than this. Right. So it's exactly what we have here, but going the opposite way. So I know I even have a colleague of mine, a very smart colleague of mine. She always hates looking at inequalities kind of different. You know, like she likes the inequalities to go one way. But yeah, so this is what we want to prove, but it's really this is bigger or equal to this, and that's exactly without the squares, that's exactly what we have. They just take the square root. This is bigger or equal to this. All right, so we've proven that. And again, the idea here is no matter what, you are not getting rid of this. It's just equal to this plus this. The best you can do is set this to be 0. You know, so we have equality. I'll just write it down. When this sequence here equals this sequence here, and that finishes the proof. What minimizes this here is exactly this sequence. All right, so up next is a really beautiful application of Parseval's theorem to carefully looking at Brownian motion. If there's demand, I'll prove all the parts about Brownian motion. It requires some serious probability theory because we are doing some real probability. But yeah, it's not too advanced that we can't do it, honestly. But it would take some time, particularly prove continuity almost surely of sample paths, prove L2 convergence and probability of the sum. But still, we'll get the expected value of Brownian motion squared. And as a homework, I'll leave you to do the covariance formula, covariance of B of S, B of T. Sorry, the covariance is minimum of S. All right, so long, take care.